We're very happy to have Alex Lubotzky from Hebrew University of Jerusalem, and he's going to speak about from Ramanujan graphs to Ramanujan complexes.
Thank you very much. I'm grateful for the invitation to be in Toronto virtually and physically. And yeah, I would like to tell you, I know that's a number theory seminar. Probably what I will tell you in number theory won't be new for you, but I want to describe something which is not very new. I will say a few words about more things which are really new, but okay, I'll tell it after that, and I will explain also why I don't want to talk about it now. I rather want to tell you a story. The story is the passing from Ramanujan graphs, which is an old story, to a more recent story about Ramanujan complexes, which are higher dimensional versions of Ramanujan graph, and some application of that, even quite surprising application, completely outside of number theory. So let's start from the beginning with this story. So what are Ramanujan graphs? Let X be a connected K-regular graph, and usually a finite one, not necessarily, but usually we'll talk about a finite K-regular graph, let's say of order n vertices. Let A be the adjacency matrix. So this means that this is n by n matrix, so that AUV is the number of edges between U and V. Usually this just means 0 or 1. I mean, but I don't mind if you really want to allow multiple edges, etc. And this is, of course, a symmetric matrix, and therefore, this is a non-oriented graph, and therefore, all eigenvalues are real numbers. And it's not difficult to see that they all lie in the interval between k and minus k. The largest eigenvalue is always k, and that's the one you get if you take the vector 1, 1, 1, 1, 1, 1, 1, or better, think of the adjacency matrix not as a matrix, but think of it as an operator acting on functions on the vertices. And then the adjacency matrix, the adjacency operator just means that if you think about it for a second, it means that A of a function at a vertex V sum up the function on all the neighbors, over all the neighbors of V, over K neighbors. And then if you take the constant function, then the eigenvalue is K, and this is the largest one. The smallest one is possibly minus K. K is always an eigenvalue. Minus K is sometimes an eigenvalue. A little exercise, minus K is an eigenvalue if and only if the graph is bipartite. Namely, there are two, you can divide the graph into two parts, and all the edges are going from one part to another, which shows you a little connection between the eigenvalue, what's called the spectrum of the graph, and its combinatorial property. For example, we can recognize whether the graph is bipartite from looking at the smallest eigenvalue. Anyway, a graph X is called a Ramanujan graph, if every eigenvalue lambda of A is either equal to K or minus K, namely the absolute value is K, or all the others are in absolute value bounded by 2 square root of K minus 1. You may ask where this number comes from, why 2 square root of K minus 1 is such a magic number. So here is a little hint. If you look at A, as I told you before, not as a matrix, but as an adjacency operator, you can apply it also to the infinite K-regular tree. Not just the K-regular graph, you can apply it to any infinite tree. And here is an old theorem of Keston, saying that if you take the adjacency operator A, apply it on the L2 functions on Tk, what is Tk? Tk is the K regular tree, and the spectrum of it is exactly the full interval between 2 square root k minus 1 and minus 2 square root k minus 1. So basically we are saying the following, and now think about it. If you take the infinite k regular tree, then the constant function 1 is not anymore an eigenfunction. Well, it's an eigenfunction, but it's not in L2. If we stick to L2, then we get only those only the eigenvalues with absolute value less than 2 square root k minus 1. So basically, we say that the graph is Ramanujan if and only if, okay, it might have the trivial eigenvalues at k and minus k, which are kind of in force of us because we live in a finite world. But all the other eigenvalues are coming from the ideal object. Just that you will memorize that, let me recall the Greek philosopher, in Hebrew we say Plato, in English I think you say Plato, that talks about the world of ideas, that every object in this world is like an ideal object in the world of ideas. And think about this K regular tree, which is, in mathematical terms, this is the universe in the language of algebraic topology, this is the universal cover of the K regular graph. Think of it as the ideal object, and well, what we say that a graph is Ramanujan is except of the two eigenvalues which are kind of in force on us because we live in the finite world, all the other eigenvalues are coming from the ideal object. Okay, but this is kind of philosophy. The importance is really coming from the following fact that the eigenvalues, it's a standard exercise in a Markov chain. If you go on random walks on graph, that the eigenvalues control the rate of convergence of a random walk to the uniform distribution. And Ramanujan graphs are those graphs for which we get the fastest possible convergence. Why? Because of an Alon-Bopana theorem. The theorem of Alon-Bopana says, okay, sorry, what one can see from elementary consideration about the Markov chains is that if the eigenvalues are very, very small, the convergence of the random walk to the uniform distribution is faster. But a theorem of Alon-Bopana says that you cannot do better than 2 square root of k minus 1. Let me maybe be here more precise. If for a single graph, you can do better than that. But if you want a family of k regular graph, an infinite family of k regular graph, and you want to bound the non-trivial eigenvalues, the best you can opt for is 2 square root of k minus 1. Now, bounding eigenvalues is very much related to a very, very important and well-known subject in computer science, which also started to have quite a bit of applications in pure mathematics, which I will not talk about today, called expanders. So Ramanujan graphs are somehow are somewhat optimal expanders. They are the best you can opt for. Okay, so this is definition, but of course everyone can make a definition, and it's not at all clear that such graphs exist. All. In fact, I want to stress, I'll show you in a minute, they do exist. By now, we know more than one method to at least to prove existent or to construct them, but there is no easy method. It's not like expanders, that random graphs are expander. This is not known whether random are Ramanujan, they are probably not. So let me show you the first explicit construction. In some sense, as an explicit construction, all the others are variants on this, and you will see that indeed quite a lot of number theory is getting to the gate. So let's fix two primes, P and Q, two different primes. Assume both congruent to 1 mod 4, but different, but they are different primes, which are both congruent to 1 mod 4. This all for convenience. It's not essential. For this audience, I'm sure the following classical theorem of Jacobi theorem of Jacobi is well known. You know, also historically, this theorem was important in a way. This was the birthday. Proving this theorem was the birthday of the old theory of automorphic forms somehow. And the theorem is a beautiful theorem, says the following: let R4 of n be the number of ways to write n as a sum of 4 squares. So it's the number of all 4 triple x0, x1, x2, and x3 in z to the 4, such that the sum of their squares is equal n. And the theorem said that this is equal exactly. It's kind of an amazing, you know, for many results like that, sometimes we have approximations. Here it's an exact solution. It's 8 times sum over all the divisors of n, but only on those divisors which are not divisible by 4. Okay, let's apply it to the prime p. So for a prime number, this is simply 8 times p plus 1, right? Because there are only 2 divisors, p and 1. Okay, but about our prime, we also assume that it is congruent to 1 mod 4. Now, if sum of 4 squares is congruent to 1 mod 4, and every square, as we know, is congruent to either 0 or 1 mod 4, so sum of 4 of them equal 1 mod 4, must be that one of the xi is odd and the 3 others are even. So let's kind of normalize and let S be the set of all 4 tuples as before, but this which sum up, the squares of them sum up P, but this time we are going to put x0, the first one, to be odd and positive. When we counted up here in Jacobi theorem, there is also multiplicity. You count plus and minuses, etc. Now, x0, we want it to be positive and odd. x1, x2, and x3 must be even and can be either positive or negative or 0. Then if you think about it for a second, this normalization kills the factor 8, and we get that the size of S is exactly P plus 1. The way I want you to think about it, that every alpha, every 4 tuples like that is an integral quaternion, is something on the form x0 plus x1i plus x2j plus x3k. And with every quaternion alpha in the set S, we also get its quaternionic conjugate is also there, right? Moreover, the real meaning is that the sum of squares is equal P. It means that the norm of alpha, namely alpha times alpha bar, is equal exactly P. So we got a set of size P plus 1. Now let's go to Q. Q was also assumed to be congruent to 1 mod 4. So there exists some epsilon in the field of order Q such that epsilon square equal minus 1, right? That's another a little number theoretical easy results. Now let's do the following. Okay, I mean, I guess you recognize that what I'm doing now, I'm splitting the quaternion algebra over FQ. And when you split the quaternion algebra over FQ, for every alpha in S, we associate the following matrix: x0 plus epsilon x1, x2 plus x epsilon x3, minus x2 plus epsilon x3, x1 minus epsilon x1. And then if you see that the determinant of this matrix is exactly the norm of alpha, namely it is P. If it is P, it means that it's different than Q. So this is the determinant is non-zero in the field FQ. So we got a non-zero determinant. So we are in the group GL2. This is not just 2 by 2 matrix, it's an invertible matrix. And I want to think about it not as an element of GL2, but rather as an element of PGL2, namely GL2 FQ divided by the center. And here is the old theorem. This was a joint work many years ago with Ralph Phillips and Peter Sarnak, that if we look at so for every one of the alpha in S, we got alpha tilde in this group. Now let's look at H to be the group generated by this alpha. Now, the group generated by this alpha is not difficult to determine what it is. You know, PGL2 FQ is a very small group. It's almost a simple group. It has a subgroup of index 2, which is PSL2 of FQ, and H is always one of the two. It's equal, actually it's kind of cute. It will be PSL2 if P is quadratic residue mod Q, and it will be PGL2 if P is not quadratic residue mod Q. All this is easy, but the substance of this theorem is that if we look at the Cayley graph of that group H, with respect to this set of generators, so we're having here a set of P+1 generators, then this is a P+1 regular Ramanujan graph. That's the substantial information, that this is a Ramanujan graph. So this Cayley graph, let me just recall what does it mean, what we mean by a Cayley graph. Cayley graph means that the elements of the group are the vertices of the elements of the group are the vertices of the graph, and we connect two vertices if one is obtained from the other by multiplication by one of the P+1 generators. So this is a very explicit construction of graphs which are Ramanujan, and they are Ramanujan graph. Now, what is the, just maybe a little remark. What is the meaning that they are Ramanujan? The meaning is that every eigenvalue is either the trivial eigenvalue P+1 or minus P+1 if it's a bipartite. And by the way, this is bipartite if and only if P is quadratic residue mod Q, or in absolute value is less than 2 square root P. And in this seminar, you immediately remember this number from Riemann hypothesis of a finite field. And in fact, the proof of this theorem really follows, I will explain in a minute, from using some result, not directly, but using some work of Ecke or Belin, which eventually boils down to use Riemann hypothesis of a finite field. So this is not accidental. Now I want to say a few words because it's a number theoretical seminar, usually I skip this part. I want to explain why this is Ramanujan. What's the name Ramanujan come from? What Ramanujan has to do, as far as I know, well, Ramanujan had some interest in combinatorics, but as far as I know, he didn't have any interest in graph theory. The reason that at the time we call this graph the property about Ramanujan is, let me explain why. Well, we all know the Ramanujan function, the product q times the q times product over all n, 1 minus q to the n to the 24, which is sigma over the tau function, tau of n, q to the n, and this power series, this is a famous function studied by Ramanujan, and Ramanujan made well, two conjectures about the tau function. One is about the multiplicity property, but the multiplicative property, sorry, not multiplicity, but the famous Ramanujan conjecture was that for every prime p, tau of p is less than p to the 11 over 2. Why, where this number come from? Then, well, this theta of z is the cusp form of weight 12 on the Hafer-up plane with respect to the modular group SL2Z, and it's an eigenfunction. It's an eigenform of the Eka operator, and the Eka operator TP for every prime p comes with the eigenvalue, which is exactly tau of p. And this Ramanujan conjecture, which I don't know if anybody really understands how he really got to this incredible conjecture, but somehow this put in a general form by Peterson, and it became known as the Ramanujan-Peterson conjecture, that if F is any Eke eigenform, and S, K, and W are the cusp forms of the Eke congruent subgroup gamma 0 n. I assume that in this audience, most of you know what is this, but if not, it doesn't really matter. I'm not going to use it. I just want to give the historical story with some Dirichlet character W. Then the eigenvalues satisfy lambda p is less than 2p to the k minus 1 over 2. And in our special case, k was 12, so k minus 1 is 11. This is the 11 over 2. But, so this is the Ramanujan-Peterson conjecture. So, okay. Still, what this has to do with our graph theory conjecture, not at all clear. But let me, again, I'm going to use some big words, and which I don't have time to explain, again, assuming that in the audience of modern number theories, much of it is known, but even if not, I just want you to see the story, not the details. Today, the Ramanujan-Peterson conjecture can be reformulated in a purely, almost purely in some sense, representation theoretic reformulation. And this is relevant for us. Why? Let A be the ring of Adels of the rational field. Let pi be an irreducible cuspidal representation in L2 of GL2A over GL2Q. I'm a bit cheating here about the definition, not to be too technical. And such a cuspidal representation is a tensor product in a restricted sense of pi p, where every pi p is an irreducible representation of GL2 QP of a p-adic. And now assume pi is such that pi at infinity at the p-adic, at the p equal infinity, assume it is square integrable. Then the conjecture is that for every p, for every prime p, the local p component pi p is tempered. Now, what is tempered? This I want to say something. Tempered really means tempered really means that the representation pi p appears in L2. It's written here, sorry. Temper means that it appears in L2 of GL2 QP. Now, what we will see later, that this pi p really appears, to start with, if it appears here in GL2A over GL2Q, then it also appears in GL2QP divided by some arithmetic lattice there. Namely, it appears downstairs in a quotient. And then the conjecture now says that everything which appears downstairs comes from upstairs. You see, now this should ring a bell, because this is exactly the phenomena I described before as a Plato phenomena. Everything which appears in the, except of the trivial eigenvalue, though which appears in the quotient graph, the graph downstairs, the finite graph, already appear upstairs in the infinite tree. So it's the same phenomena here, that a representation which appears in the quotient really appears also upstairs. And this is really the essence of the Ramanujan conjecture. So Ramanujan graphs is a kind of representation theoretic, I would say, appearance of the same philosophy. Okay, this is, if you are familiar with this language, it might help you. If not, just, it's kind of justification for the name. Anyway, let me just mention that what was called Ramanujan Peterson conjecture is Deligne theorem. Deligne, when he got the Fields medal basically for proving the Weil conjecture, and he deduced from it also the Ramanujan Peterson conjecture. Now let me go back after this kind of philosophical explanation to the name and explain you where are these graphs with the Jacobi theorem, where are they come from? Because I'm sure you understand that you don't just wake up one morning and say to yourself, let's take these generators and they will form a nice graph. Let's check whether this is Ramanujan or not. There is really kind of a story how to get to this graph, and I want to reveal what is this story. So where this graph, which I called before X, P, and Q, this Cayley graph, depending on the primes P and Q, where do they come from? Okay, let F now be the field of p-adic number, or you can take the characteristic P analog, the local field of the Laurent power series over Fp. Let O be the ring of integers in F, either the p-adic integer or Fp double brackets T. Let G be the p-adic Lie group PGL2F. K, the maximal compact subgroup, which is PGL2O. And let's look at the symmetric space, right? Just like we are used to do over the real number G mod K, the simple Lie group divided by a maximal compact subgroup give us a symmetric space. Here in the p-adic case, we have the Brouwer-Titz building the Boatitz theory, where in this special case, the Boatitz building is just a tree, the Boatitz tree. And in this case, this is just P+1 regular tree. So you feel like we are getting some combinatoric, some graph theory is coming to the game. Let gamma be a discrete co-compact subgroup, the so-called lattice in the group G. Now we can look at G mod K, divide G by K from one side, and divide by gamma from the other side. Now, when we divide the G by K, we got the tree. This is the P+1 regular tree. Now we divide it by gamma also. So this is like dividing a tree by an action of a group, we get a graph. But this was a co-compact lattice, namely G mod gamma is compact. So this is a compact graph. But graph is a discrete object. So a compact graph means just a finite graph. So by this complicated way, we just get a finite P+1 regular graph. Okay, but hold on, don't guess that these are the Ramanujan graphs, not at all. Because if you just do it with an arbitrary lattice, every finite P+1 regular graph can be obtained like that. In order to get a Ramanujan graph, this is a much deeper story. And here is a theorem. This graph, G mod K mod gamma, which is T mod gamma, this finite P+1 regular graph is a Ramanujan graph if and only if every infinite dimensional, irreducible, spherical subrepresentation of L2 of G mod gamma as a G representation is tempered. You remember the word temper, right? Tempered, well, one of the definitions that matrix coefficients are in L2 plus epsilon, but weakly contained in L2G. Okay, I don't know if you're familiar with this language, so that's fine. If not, it's not really important. What's important for me here that you see that this down-to-earth, simple down-to-earth property of a finite graph being Ramanujan, namely all the eigenvalues are bounded by something, is equivalent to some kind of a fancy results on infinite dimensional representation theory. That's kind of the amazing in this story. We go to an infinite dimensional unitary representation L2 of G mod gamma, and if we understand the decomposition of it, then we understand that this finite graph is Ramanujan. So as it's written here, so the combinatorial property of being Ramanujan is equivalent to a purely representation theoretical statement. And that's actually this representation theoretical statement, if you remember the Satake version of the Ramanujan version, is really a number theoretical results. I mean, it's not, here I want to be careful, it's not equivalent to the full Ramanujan Peterson, but it will be a corollary or a corollary of it. Okay, luckily, when we did this work, we had the theorem of Deligne was on the shelf waiting for us. And from the theorem of Deligne was talking about the Adels, etc. But you can deduce the following local results. His results is global, and you can deduce the local. It's kind of interesting that I don't know any direct local proof for these results. It's somehow the way is to go to the global and then to deduce it to the local. And here is the theorem of, here is a corollary of the theorem of Deligne. If gamma is an arithmetic lattice of PGL2QP and gamma I is a congruent subgroup, then every irreducible, infinite dimensional spherical sub-representation of L2 of G mod gamma is tempered exactly that condition that we needed in order to show that we get a Ramanujan graph. And so the corollary is that if we take this Boatitz tree divided by such a congruent subgroup, we get a Ramanujan graph. And the example which I showed you at the very beginning of this talk are just special case, choosing a very particular example, a nice example of such arithmetic lattice gamma, and implementing this theorem, this corollary to that graph, we deduce that this is an explicit construction of Ramanujan graph. Okay, I should rush now. It turns out that these graphs are wonderful from a combinatorial point of view at the time when we did only for the Ramanujan property, but they solve a good number of other parts. Now I want to go to the second part of the story, and this is Ramanujan complexes. But now in the way I presented to you, even though complexes are much more complicated, I think you can see the point of the generalization. Why? Now we'll go to higher dimensional. Instead of looking at PGL2F mod K, which gave us the tree, we look at BD of F, the Boatitz building, G mod K, but this time G is PGLD of F, modulo the maximal compact subgroup PGLD of O. Just like in the case D equal 2, this was a tree. Now we are getting a D minus 1 dimensional contractible simplicial complex. It's an infinite simplicial complex with some incredible properties of symmetries, etc., generalizing the notion of tree to an higher dimensional situation. Now there is a little story here, which again, it's a bit technical. I must say something about that, but I will rush. The vertices of the building comes with the natural colors, which are the best way to think of these colors is they come with D colors, which are elements of the finite cyclic group Z mod D. And they obtain like that, doesn't matter even. And now, you see, if you remember, in the case of D equal 2, we had one operator, the adjacency operator. Here we are going to define D minus 1 operators. For D equal 2, we had one operator. Now we will have D minus 1 operators from L2 of BD of F to L2 of BD of F, define for every I between 1 and D minus 1, AI of F at a vertex X is the sum of the neighbors, but not all the neighbors, only those neighbors so that the color of Y minus the color of X is equal I. The colors are element of the finite cyclic group here. So this gives us D minus 1 operator. The sum of them is the adjacency operator of A. But we really want to look at all D of them, all D minus 1 of them together. Now it's a bit more complicated because the AI are normal commuting operators, but not necessarily self-adjoint. So in fact, the adjoint of AI is a D minus I. So the eigenvalues are not necessarily real, but they are at least normal commuting operators, so we can diagonalize all of them simultaneously. So if we diagonalize them simultaneously, we can think about the spectrum of the complex, the spectrum now of the infinite complex, You see, I'm looking for the analog of Kasten theorem. Kasten theorem told us that the spectrum of the K regular tree is the interval between 2 square root K minus 1 to plus 2 square root of K minus 1. Now, the spectrum is not just a set of real numbers. This is a subset of C to the D minus 1 because I have a D minus 1 operator acting and commuting and I diagonalize them simultaneously. Am I getting what the spectrum, which is a set sigma D in this set? It's known, not it was known. The people in representation theory, classified this, described this set. I don't want to go to the details. I want just to say that now you can guess what will be the definition of a Ramanujan complex. You remember what was a Ramanujan graph? Ramanujan graph was such a quotient of the tree such that all the non-trivial eigenvalues are in the spectrum of the tree. Now, if we divide the building by a co-compact discrete subgroup, we call it a Ramanujan complex if every non-trivial eigenvalue, now what is an eigenvalue now? Eigenvalue now is not a number. Eigenvalue is a vector with D complex numbers, right? The eigenvalue of this D minus 1 tuple of operators is inside the good set. You know, this is like the Plato philosophy, right? Every eigenvalue downstairs is coming from upstairs. Then we will call it Ramanujan. Okay, I'm a bit, I'm telling a story today. So I won't tell you what means non-trivial eigenvalues, what means trivial. In the case of D equal 2, we had 2 trivial. Now we have D trivial eigenvalues, and they are easily understood. So that's not the interesting. One can prove even a Nombo-Pana type theorem. This was proved by Lee that you cannot do better. If you want to bound the eigenvalue in a region as small as possible, then the eigenvalues of an infinite family of such complexes, there are only countably many, but the closure of them will contain sigma D. So the best you can opt for is that they will be bounded by inside this sigma D. And here's a theorem. This, again, an old work with Beth Samuel, which unfortunately passed away shortly after that, and Uzi Vishna, that the complex is BD mod gamma is Ramanujan, if and only if every infinite dimensional irreducible spherical sub-representation of L2 of PGL DUF mod gamma is tempered. Exactly the same statement as before. But of course, this theorem is correct. We made the definition of Ramanujan so that this theorem will be correct. Exactly to understand what is the combinatorial meaning of such a result that these representations are tempered. Why did we do it? We did it exactly after the work of Laforgue. The work of Laurent Laforgue, because I'm going to mention his brother soon. Laurent Laforgue got the Fields Medal for proving the analog of Deligne in characteristic P, but also in higher dimensions. So basically, a corollary of the work of Laforgue was that in positive characteristic, if gamma is an arithmetic subgroup of PGL DF and gamma I is a congruent subgroup, then under some restriction, every sub-representation, every spherical sub-representation of L2 of G mod gamma I is tempered, which means that now the theorem of Laforgue enables us to work to get Ramanujan complexes, and we got explicit construction of them, etc., etc., etc. Okay, I have to admit that at the time when we did it, well, Beth Samuel was a student at Yale, Uzi Vishna was a postdoc there. I visited there for a while, and then some of Beth asked me for a problem. I told her, you know, we got a lot of mileage from this theorem of the Lin combinatorial application. There must be some combinatorial meaning to the theorem of Laforgue, and we set to understand the combinatorial meaning, and that's what we came up with. But we didn't really have any goal in mind, like why this will be interesting really from combinatorial point of view. And I like to joke that the government of India understood that still our paper is important, and they called up an area in India which is called Ramanujan complex, just like the name of our paper. Now I want to jump many years after. Well, not really. I'm going now. I have only 10 minutes or 12 minutes, but I'm starting now a new talk. The new talk is about a dramatic application of these Ramanujan complexes in a completely unexpected direction. Okay, I probably will not have time. By now there are a few applications. Maybe let me make a little propaganda because I will not have time at the very end. I will make a propaganda to. Do you see now the slides showing the breakthrough locally testable codes with constant rate?
Yes.
So let me call your attention to a lecture by Irit Binur, which will be in the 6th of October. So I don't want to, I just do a little advertisement. Very, very recently, really like a few weeks ago, this circle of ideas of using Ramanujan graph, an I-dimensional version of them, was found out to have a fairly dramatic application in error correcting codes to find the so-called locally testable code. This was an open problem for 30 or even more, 30, 40 years. And some ideas which related to that were found useful also in that direction, but the paper is not even yet on the archive, but she will talk about that in this sequence of I think twice a year they have in the Simon Institute in Berkeley breakthroughs in computer science, and she will, Irit Binur, will talk about, this is one of my co-author on that, and she will talk about that work over there, and that will be related. She will probably present it from a very different perspective, but you will see that the Ramanujan graph and complexes are coming up also there. But now I will go to an even more unexpected application in kind of geometry or topology. A solution to a problem of Misha Gromov. So let me, again, I'm just going to tell you this as a story. The story actually started in '84. Borosh and Furedi at that time, by now they are fairly well-known, one is mathematician, computer scientist, but anyway, doing this type of an ergosh, they proved as a response to a problem of Erdos. Now, if you lost me, by the way, I'm starting now a completely new talk, so you can come back again. Till the very end, it won't be, you won't see that it's related to the previous talk. Borosh and Furedi proved the following beautiful theorem. Assume somebody give you a set P in the plane, in R square of size n, then there exist n choose 3 triangles, which are determined by the n choose 3 by the endpoints, right? Every 3 points determine a unique triangle. Draw all these triangle, and the claim is that there exists a point Z, which is covered by 2/9 of them, independent of the choice of P, independent of everything. It's a beautiful theorem in convexity theorem. Whatever you will do, it won't help you. 2/9, at least 2/9 of them will intersect, and it was later on was proved that 2/9 is the optimal. Shortly after that, Barani proved an I-dimensional version of this theorem, namely fixed D, greater or equal to. Then there exists a constant CD depending only on D, such that if P in R to the D is a set with endpoint, again, every D plus 1 points determine a simplex, a unique simplex is determined by every D plus 1 point, then at least CD times, at least there is a linear fraction of them depending only on D, which meets each other. Namely, there exists a point which is covered by at least CD and choose D plus 1 of the D simplices that determined by P. Again, a beautiful theorem in convexity theory. Oh, sorry. Few years ago, Gromov came up with an amazing theorem, but this theorem completely changed the point of view on this type of problem of Borosh, Foredi, and Barani. Gromov, let me give first the definition of Gromov is in a language which we are using now, not exactly the language which Gromov used. But let's say the following: a simplicial complex X of dimension D as the epsilon geometric, respectively topological, overlapping property, if for every map from X0, namely you take any map from X0 to R to the D, X0 means the vertices of the simplicial complex, and every affine extension of F to a full, okay, basically there is a unique affine extension. Once you have a map from the point of simplicial complex to R to the D, you know, then you can extend it to the lines between them in a linear way, you can extend it to the triangle, etc. And this is for the geometric definition. For the topological definition, you say for every continuous extension. Now you have plenty of such extensions, uncountably many possibilities. And then he says there exists a point Z in R to the D, which is covered by at least epsilon proportion of the D cells of X, of the images of the D cells of X. And now for a family of such D complexes, we'll call them geometric expanders or respectively topological expanders if they all have this property with the same epsilon. Those of you who know the definition of expander graphs are invited to think why this is a generalization of this notion. Anyway, the theorem of Borosh and Foredi for D equal 2 and the Barani for all D can be now said that the complete D simplicial complex on the end vertices are geometric expanders. They have this property. And Gromov made up okay, Gromov but Gromov wanted ask, if you take the complete D-dimensional n vertices, so you see it as n vertices, but it has n choose 2 edges, it has n choose 3 triangle, etc., etc. He asked, can you get a family of such, first of all, he proved an amazing theorem. It's really amazing theorem. If I would have more time and if I would have a blackboard, I will try to draw you, just try to draw for yourself the meaning of his theorem for dimension 2, and you will see that it's very difficult to believe that this theorem is correct. He proved that the full simplicial complexes are also topological expander. This is a very clear meaning. You put endpoints on the plane and you start to do triangles between every three of them. You can make the triangles to be very, very, very narrow. Make them as narrow as you want. And still there is a common point of intersection of 2/9 of them. It's amazing. It's really an amazing theorem. But he put forward an even more difficult question. Can you find simplicial complexes like that of bounded degrees, so that every vertex is only in a bounded number of edges? And few years after that, in a joint work with Laforgue, this time is the brother, Vincent Laforgue, and Asaf Naor, and Janusz Pach, and Jacob Fox, they proved that those Ramanujan complexes that I mentioned to you before are geometric expanders. So I have to say that I didn't know about this work before. Then somebody called my attention that they were using our work, so I was very happy. I started to look at that, and then they left open the question: can you find topological expander, the much more difficult property, with bounded degree? And actually, I talked with Gromov, and he was not sure if they really exist at all. And eventually, it turns out that these Ramanujan complexes are solving also this problem, but in a very strange way. I mean, you may expect that I'm going to tell you, the d-dimensional Ramanujan complexes, which are also topological expanders. They have this Gromov property. I don't know that. That's still an open problem. What we managed to prove, this was first of all work of Tali Kaufman, David Kashdan, and myself for dimension 2, and then my student Evra with Tali Kaufman did it for every D. We managed only to prove the following. Fix some, should be really prime P, very large, very, very large. The D skeletons of the D+1 Ramanujan complexes are D-dimensional topological expanders. We don't know if the Ramanujan complexes themselves are topological expanders. But we say, forget about the top structure, just take the D skeleton. Okay, so you get a D. Because it's eventually done for every D, this is a full solution to Gromov problem, though we are not sure. That's not really what we wanted. We wanted to prove that the full Ramanujan complexes are topological expanders, just like Gromov and his co-authors proved that they are geometric expanders, and this we still don't know. So there is still a lot of thing to do here. Let me just mention that there is going to be a conference in late October, 26 up to 27 up to 29 in New York in the Simon Institute about I-dimensional expanders, which will relate it to all this I-dimensional theory. Those who want to attend either physically or remotely, please maybe write to me almost immediately, because the Simon Foundation has the policy that you must register it in advance. If you want to come there, they even provide you, I think, a free hotel, not travel, but hotel in New York. But even if you want to attend it remotely and to listen to the lecture, you have to register it, and they're pretty strict about that. And I try to convince them not to be so strict. at this time, but they want the registration to be till the 24th of September, so it really should be done almost immediately. So if you will write directly to me, I'm like the organizer of this workshop, so I hope they will listen to me and will add new people to the list. They are very well organized, not like our like us as mathematicians. So sometimes they're a bit tough, but they are very generous, and it's fantastic organization. It's the second time I'm doing something like that with them, so I'm sure it will be a nice event. Okay, so I finish my my story, and thank you very much for the invitation, and thank you very much for your patience.
Thank you for a great talk. We thank Alex. Any questions? Yeah, please.
Yeah, so Alex, firstly, nice talk, and I liked your informal story approach to the topics. It was nice. I was wondering whether this 2 nines or the other constant that occurs more generally in the Gromov setup is supposed to have any topological or geometric meaning.
It certainly is, but it's not understood. The 2 9 is amazing. The 2 9 is the same number for the geometric overlapping and for the topological overlapping. So Gromov proved the same theorem with the same content, even though you would expect that in the topological it will be much smaller, maybe. It's not known. So we can really have, we can define now what would be the best constant for D. It's not known that in general CD, for the geometric CD and the topological CD, are they the same or not in general? It's also not known what is the rate of CD. I mean, it's not difficult to show that CD goes to 0 when D goes to infinity, but it's not known what's the rate. What is amazing, by the way, that Gromov proved is theorem for the topological expansion with a better constant than Barani proved for the geometric. So it's really incredible. Now, I didn't get to the proof of Gromov, which is also amazing. The proof of Gromov is really using some cohomological methods over the finite field of order. Now, this opens up the connection with the computer science, which I gave some promotion. This, nowadays, we call it co-boundary expansion, this cohomology mode 2, and the results in cohomology mode 2 were the starting point for me of relating it to the subject in computer science called properties testing. Property testing is one of the deepest, if not the deepest area in computer science. You maybe heard the nicknames PCP theorem. The PCP theorem is probably the deepest theorem in theoretical computer science in the last few decades. And locally testable code is a kind of a variant of that. What you want to identify, you get a huge amount of information. Like in error correcting codes, you get a very long vector of bits, and you want to check whether this is a legitimate word, but I allow you to read only 60 bits out of the n bits, and you have to tell me whether this is correct, whether it's in the code or not, in a random algorithm, which will 90% of the time will be correct. You see, so this is kind of an amazing, somehow theoretically you think that it's unbelievable, that this is impossible. It turns out that this is impossible in a way by the same thing why Gromov's theorem is correct, why Ramanujan complexes exist. You see, the feeling, let me say another philosophy. The feeling already with Ramanujan graph, but it's much more so with Ramanujan complexes, is that on one end, this object behave like random. The Ramanujan graphs are kind of or expander in general are approximation to random graphs. You think of as random. On the other hand, they are very well organized. They are Cayley graph. In these Ramanujan complexes, we have structure of them with a Cayley graph and a lot of symmetries from all places. So you see, it's random and organized and well ordered at the same time. So this is like a contradiction, right?
Mm-hmm.
And just like in mathematics, if you start with a contradiction, you can prove everything. So if you start with something which is almost contradiction, you can prove a lot. You can prove a lot, maybe not everything. And I think that this is really behind the success story of this object, that they are holding very kind of contradictions, almost a contradiction within them.
Could I ask one more question, Payman?
Sure.
Yeah. So in the definition of the Ramanujan complex, I wonder, I mean, you're looking at, so you have the rank of the group, and then you're taking the top, you're taking the simplices of the top rank, right?
Yeah.
But could you do something in between? I mean, for lower rank?
Okay. It's you asking. You see that I say you are an expert. You're asking a wonderful question. I mean, I gave here the definition that we started with, which was the one, and I presented it as a generalization of the Ramanujan graph. And then we took the colored Eka operator. Now you can really give many different definitions. In fact, the conference I'm talking about, which is a second in a series, there was such a conference in the Simon Foundation 2 years ago, was exactly by people coming from number theory, from combinatorics, from computer science, looking for what is the right notion of high-dimensional expanders. Now, in a way, there is no right notion. The big success of expander graphs is that there are many equivalent definitions. Each one of them can be extended to an high-dimensional in more than one way, and you start to ask yourself whether all these possible definitions are equivalent to each other or not. For example, there is the geometric expander, logical expander, boundary expander, there are many more. So there are a number of people who study random walks on the top layers or random walks on the high-dimensional sets. And in fact, there was also a big breakthrough in combinatorics that by using these random walks, it inspires some people to solve another long-standing problem there. So nowadays, there are many people getting to the game from different angles and study. But now we are still, all this area is in the stage of formation, so it's not clear where we are going to.
Interesting. Thank
you. Any other questions? I don't see any questions in the chat box, but if anyone has any questions, they can just unmute themselves and ask. Okay, if there aren't any other questions, we'll thank Alex again for a very nice talk.
Thank you very much. Thank you. Thank you very much.
Thanks, Alex, for making it to Toronto. I look forward to seeing you.
And Kumar, I'll see you at 3 o'clock, right? I'm coming downtown to see you. Good, great. See you later.